So homework 4, number 1, we have 3 matrices, A, 2 minus 3, 5 minus 7. And the determinant, so if you have a matrix A, which is A, B, C, D, the determinant is of A is AD minus BC, and SL2Z is the set of all matrices A, where A, B, C, and D are integers, and the determinant is 1. So for example, for this matrix, the determinant is 2 times minus 7 minus minus 3 times 5. That's minus 14 minus minus 15 is plus 15 is 1. I should have put a comma in when 1A, because what's stated is still correct, but I really meant you to check that all 3 matrices are in SL2C. B is the matrix 2, 5, 5, 13. The determinant of B is 2 times 13 minus 5 times 5, which is 26 minus 25, or 1. C is the matrix 4, 1, 19, 5. The determinant of C is 4 times 5 minus 19 times 1 is 20 minus 19, which is 1. So all 3 of these matrices are in the group SL2C, and the rest is just doing some matrix multiplication. So if you take AB, that's the matrix A, times the matrix B. When you multiply, you get 4 minus 15 is minus 11. 10 minus 39 is minus 29. 10 minus 35 is minus 25. 25 minus 91, which I think is 66. Is that right? 91 minus 25, yeah, 66. So the determinant of AB, if I did this matrix multiplication correctly, let me just double check. 2 minus 3, 5 minus 7, 2, 5, 5, 13. So I get 4 minus 15. 10 minus 39 is minus 29. 10 minus 35 is minus 25. And 25 minus 91 is
minus 66.
25 minus 91 is minus 66. Okay. So the determinant is minus 11 times minus 66 minus minus 29 times minus 25. So 11 times 66 is 726, I think. And minus, the minus signs cancel. 25 times 29. So 28 times 25 is 700. 29 times 25 would be 725, and the difference is 1. So you do the matrix multiplication, and you get the result. And the same with all the others. It's just a calculation. And the point of the calculation is just to get some practice multiplying these matrices. In terms of the inverses, we proved that if you have a matrix A, B, C, D, with the determinant of A equal AD minus BC equal 1, then the inverse is exactly D minus B minus CA. So it's good to memorize that, but in any case, you can always write it down and look it up. So in the case that A is equal to 2 minus 3, 5 minus 7. A inverse is minus 7, 3 minus 5, 2. And you can check 2 minus 3, 5 minus 7 times minus 7, 3 minus 5, 2. This is minus 14 plus 15, 6 minus 6, minus 35 plus 35, 15 minus 14. And the others are exactly the same. There's nothing to do other than do the calculation. And again, if you have Maple, which I strongly encourage everyone to get because you can get it for free from the CUNY website, you can do matrix multiplications in Maple and check everything. Any other questions about problem number 1? Okay. Problem number 4 you asked about. You have a matrix A, B, C, D in M2 of R. This means that A, B, C, D are in R, not integers, but the real numbers. And the determinant is still AD minus BC. And suppose that this determinant is non-zero, I claim that A inverse, it's almost the same as the inverse of a matrix with determinant 1. If A had determinant 1, the inverse would be D minus B minus CA. And in the case when the determinant is not 0, but not necessarily 1, you have to divide by the determinant. That means divide every element by the determinant. So let's look at an example. If A is the matrix 1, 2, 3, 4, the determinant is 1 times 4 minus 2 times 3 is minus 2. So according to this formula, A inverse will be 1 over minus 2 times 4 minus 2 minus 3, 1, which is just means multiply every element, every coordinate of the matrix by minus a half. Minus 2, 1, 3 halves, minus a half, right? This means when you multiply a matrix by a number, you multiply every coordinate of the matrix by a number. So minus a half times 4 is minus 2, minus a half times minus 2 is 1, minus a half times minus 3 is 3 halves, and minus a half times 1. So let's check. So A inverse, 1, 2, 3, 4, minus 2, 1, 3 halves, minus a half, I get minus 2 plus 2 times 3 halves, and 1 times 2 times minus a half. Sorry, 1 plus 2 times minus a half. This is minus 6 plus 4 times 3 halves. And the fourth coordinate is 3 minus 4 times minus a half. Sorry, 3 plus 4 times minus a half. This is minus 2 plus 3, 1 minus 1, minus 6 plus 6, 3 minus 2. That's the identity. So that's the whole story. It's just fun with matrices. Other questions about this?
Professor, can you also try the number 7 and 8?
So number 7 is to look at the set of matrices, which for whatever reason I call gamma 0 of 2. This is a capital Greek letter gamma. This is all A, B, C, D in the group SL2Z, where, so the fact that they're in SL2Z means A, B, C, and D are integers and AD minus BC is 1. So that's what this means. But we only look at those matrices where C is even. And we want to prove that this is a subgroup, that it's a group all by itself contained in this bigger group, because not every matrix in SL2Z satisfies this condition. So for example, the matrix 5, 3, 3, 2 is in SL2Z, but because 10 minus 9 is 1, but this coordinate right here is odd. So this is a matrix in SL2Z, but it's not in this set of matrices where this lower left-hand component is an even number. And so what does it mean to say it's a subgroup? We have to show, first of all, the identity 1, 0, 0, 1 is in gamma 0 of 2. But this is true because 0 is even, right? You look at this coordinate, it's even. So the identity matrix is there. Suppose you take a product of two matrices, A, B, C, D, and E, F, G, H. So we know the product is an SL2Z. We just have to show that the product has this coordinate even. It doesn't matter what this is. It doesn't matter what this is. It doesn't matter what this is. What is this coordinate? This coordinate, when you do matrix multiplication, is CE plus DG. And we know C and G are both even. So this is even and this is even. So this is even. So the product is in this subgroup. So this set of matrices contains the identity and is closed under matrix multiplication. If you take A, B, C, D in SL2Z, call that A, then we already know A inverse is D minus B minus C A. And if C is even, minus C is even. So this will also be in gamma 0 of 2. So this set of matrices contained in SL2Z is closed under multiplication. It contains the inverse of each element and it contains the identity. And that's what we needed to prove. To prove it's non-abelian, you can just show that, I don't know, take two different matrices. I'm going to try and make them maybe not too hard. 1, 1, 1 minus 1, 2, 1. Minus 1, minus 1. So that's a matrix which has determinant 1, and this is even. And suppose we take, I don't know, 1, 0, 0, 1. So multiply these two together and then multiply them in the opposite order. Oops, got a 1. So this is determinant 1. This is determinant 1. When I multiply these, I get minus 1, minus 1, minus 2, 2, 3. And when I multiply these, what do I get? I get minus 1 plus 2, minus 1 plus 1, 2, 1. So these are different. So these are matrices in this group, which I called gamma 0, 2. And the product of one times the other is different from the product of the second times the first. So that proves it's not abelian. Okay. Any questions about that? Let's see, was there another question you wanted me to do?
Number 8.
Okay, so again, the method is going to be the same as for number 7. In this case, we're looking at a set, I just called a gamma of n, which is all matrices A, B, C, D in SL2Z, where A and D are both congruent to 1 mod n, and B and C are both congruent to 0 mod n. Okay. So this means that this number n divides B and C, and when you divide A and D by n, you get a remainder of 1. So for example, the identity matrix 1, 0, 0, 1 is in gamma of n, because these two numbers are congruent to 1 mod n, and these two are congruent to 0 mod n. So this set contains the identity. Let's see if this set of matrices is closed under multiplication. So suppose we have two matrices, A, B, C, D, and E, F, G, H in gamma n. When you multiply them, you get AE plus BG, AF plus BH, CE plus DG, and CF plus DH. So let's see, what can we say? Let's look at AE plus BG. AE plus BG, B is congruent to 0 mod n. So this is the same as AE plus 0 mod n, which is just AE mod n. And because these two matrices belong to this set, we know that A and D and E and F are all congruent to 1 mod n. And the off-diagonal elements, B, C, F, G, they're all congruent to 0 mod n. I mean, that's why I could cancel this. Now, A and E, they're both congruent to 1. This is congruent to 1 times 1, or 1, mod n. So this coefficient is 1 mod n. What about this coefficient? CF plus DH. Well, C is 0 mod n. So this is congruent to DH. Oops, what happened to H? Oh, CE plus DH. Let me do this arithmetic right. So A, D, E, and H. That's what I should have written. That's fine. So D and H are both congruent to 1 mod n, and 1 times 1 is 1. So this coefficient is also 1 mod h. And what about the off-diagonal coefficients? AF plus BH, F is 0, and B is 0. So that's congruent to 0 mod n. And this element, CE plus DH, C is 0, sorry, CE plus DG. Should have written it down correctly. CE plus DG, C and G are both 0. So this is 0 plus 0, which is 0 mod n. So the product of two matrices in this set is in the set. What about the inverse? The inverse of A, B, C, D minus 1 is dA minus B minus C. And A is congruent to D is congruent to 1 mod n. Here, these are the same numbers. And minus B and minus C are also congruent to 0 mod n because B and C are 0 mod n and minus 0 is 0. So you check that this set of matrices contains the identity, it's closed under matrix multiplication, and for every matrix in this set, the inverse also is in the set. And that's what it means to be a subgroup. And again, just picking almost any pair of matrices in the set and multiplying in the order AB and then the order BA, you will get that it's non-abelian. Right. Any questions about that? Okay. So let's go back to the subject of this part of the course, which is congruences. So we say A is congruent to B mod M if M divides A minus B. And we proved that congruence, so again, we can always just take M to be a positive integer. Congruence modulo M is an equivalence relation. And what is called the congruence class of an integer A modulo M is the equivalence class of this relation. Namely, it's the set of all numbers B such that A is congruent to B mod M. And this is the same as saying if A minus B, let's say B is congruent to A mod M. If B is congruent to A mod M, that means B minus A, it's the set of all B such that B minus A is some multiple of M, which is the set of all B such that B is A plus M times Q. Here, Q can be any integer. So you can think of this as kind of an infinite arithmetic progression. You have the number B, the number, you have the number A plus M, A plus 2M, A plus 3M, and so on forever. And also in the negative direction, A minus M, A minus 2M, A minus 3M, and so on forever. So on the number line, the congruence class is A plus M, A plus 2M, and so on, A minus M, A minus 2M. You can think of this as a doubly infinite in both directions arithmetic progression. Okay. That's what a congruence class is. And if you take any number A, so by the division algorithm, that is by long division, if you take any number A and divide it by M, you get a quotient q times m plus a remainder, where the remainder is between 0 and m minus 1. So a minus r is q times m. So a is congruent to r mod m. So every integer is congruent to an integer between 0 and m minus 1 mod m. And these are the numbers, the integers from 0 to m minus 1. And if you take any two of them, the distance between them is strictly less than m. So no two of these numbers can be divisible by m unless they're the same. So every congruence class is of the form, let me write it, r plus mz. So this just means, see, I could also write this as, well, r plus mz. Mz is just the set of all multiples of m. So that's 0, m, 2m, 3m, minus m, minus 2m, and so forth, which is also the congruence class of 0. So r plus mz is everything of the form r plus mq, where q is an integer. And we use the following notation: z mod mz is the set of congruence classes modulo m. So that's the congruence class of 0, congruence class of 1, the congruence class of 2, congruence class up to m minus 1. So what we've done is take the set of integers z and partition it up into m pieces. Mz, 1 plus mz, 2 plus mz, up to m minus 1 plus mz. So this set of congruence classes, among other things, is a partition of z. It's a partition of this infinite set into a finite number, exactly m pieces. Each piece happens to be an infinite set of integers, but z mod mz is a finite set. It's a finite set consisting of m elements, and each element in z mod mz is a congruence class, which means an infinite set of integers. So this is a very important picture to have in your head, and it's a model for a lot of what we will do in more or less abstract algebra, but this is really a very concrete example of more general phenomena. Okay. Any questions about this? Right. This is what we talked about on Monday. And with congruences themselves, remember, we proved the following. So congruences to the same modulus m, it has to be the same, can be added and multiplied. This means that if A1 is congruent to A2, sorry, let me write it like this. Well, if A1 is congruent to A2 mod m, let me just see which notation I used in my notes. I did it slightly differently. So well, it doesn't really matter. A1 is congruent to B1 mod M, and A2 is congruent to B2 mod M. Then I can add the congruences. A1 plus A2 is congruent to B1 plus B2 mod M. And A1 times A2 is congruent to B1 times B2 mod M. Now, let's see. In algebra, we like to solve equations. So here's a linear equation in one variable. Solve the equation 6x equals to 5. Of course, you have to know, what does it mean? Where you look for solutions? In Z, in the integers, there's no solution. There's no integer such that 6 times the integer is equal to 5. In the rational numbers, there is a solution. X is equal to 5/6. So when you ask about solving an equation in algebra, you have to know where you're looking for the solution. What about, but we're looking at congruences, so what about linear congruences? So an example of a linear congruence, so the general linear congruence would be, given a modulus M, we want to solve the congruence AX congruent to B mod M. Right? I mean, the general linear equation is AX equals B, but if you're looking at congruences mod M, to solve this mod M really means you're looking for an integer where AX is congruent to B mod M. So suppose we take 6x congruent to 5 mod 13. Can we find an integer that solves this equation? And anyone have can anyone find an answer? Can you find an integer x such that 6x is congruent to 5 mod 13? I mean, you can always start running through the numbers. Does 0 work? Well, if you let x equal 0, 0 congruent to 5 mod 13. Which is 0 congruent to 5 mod 13. Doesn't work. Well, if we look at x equal 1, 6 times 1 congruent to 5 mod 13. Well, 6 minus 5 is 1. It's not 0 mod 13, so this doesn't work. Let's try x equal 2. 6 times 2, is that congruent to 5 modulo 13? That means it's 12 congruent to 5, or 12 minus 5 is 7. Is that divisible by 13? No, that doesn't work. What about x equal 3? 6 times 3 congruent to 5 mod 13. 18, is that congruent to 5 mod 13? Well, 18 minus 5, wow, that is 13. It's 13 times 1. So this congruence (6x) congruent to 5 mod 13, one solution is x equal to 3. What about another solution? Well, if you take any number x congruent to 3 mod 13, because you can multiply congruences, then 6x is congruent to 6 times 3, or is congruent to 18, which is congruent to 3 mod 13. So any x congruent to 3 mod 13 works. So another solution is x equal to 16. Let's check. 6 times 16 is 96. So 6 times 16 minus 5 is 96 minus 5 is 91. And if my arithmetic is correct, this is a multiple of 13. It's 7 times 13. So 6 times 16 is congruent to 5 mod 13. So x equals 6 is a solution. What is another solution? Well, minus 10 is congruent to 3 mod 13. So suppose I had x equal minus 10 is 6 times minus 10 congruent to 5 mod 13. That's minus 60. Is that congruent to 5 mod 13? Well, minus 60 minus 5 is minus 65. And if your arithmetic is good, this is minus 5 times 13. So this is okay. So we found one solution, x equal to 3. Another solution, x equals 16. Another solution, x equal minus 10. And in fact, there are infinitely many different solutions in the integers, infinitely many integer solutions, because there are infinitely many numbers that are congruent to 3 mod 13. Any questions about this? All right. So what I just showed is that the linear congruence, AX congruent to B mod M, that's what we're considering. So for our first example, 6x congruent to 5 mod 13 has, for example, the solution x congruent to 3 mod 13. Any number in this congruence class is a solution. In fact, this infinite set of numbers is the only solution. How can we prove that? So suppose x and y are integers, and 6x is congruent to 5 mod 13, and 6y is also congruent to 5 mod 13. So by the symmetry, 6x congruent to 5, 6y congruent to 5, 6x congruent to 5, it means the same as 5x congruent to 6x mod 13. By the transitivity of congruences, if 6y is congruent to 5 and 5 is congruent to 6x, 6y is congruent to 6x mod 13. What does that mean? That means 6y minus 6x is some multiple of 13, which means 6 times y minus x is some multiple of 13. So 13 divides the product of the integers 6 and y minus x. But the greatest common divisor of 6 and 13 is 1. They have no common factors. So by Euclid's lemma, if a number divides a product and it's relatively prime to one term, then it divides the other. So 13 divides y minus x, or in the language of congruences, y is congruent to x mod 13. So any two solutions of this linear congruence are congruent mod 13. If you let x equal 3, that's a solution. That means any other solution is congruent to 3 mod 13. So therefore, every solution y satisfies y congruent to 3 mod 13. So not only did we find one solution or one congruence class of solution, but we proved we found every solution. That's all of it. Okay. Let's take another example. Instead of maybe 6x congruent to 5 mod 13, suppose we consider 6x congruent to 5 mod 14. Can anyone find a solution of that linear congruence? Well, let's see. So if x, the integer x, is a solution, then 6x minus 5 has to be a multiple of 14. So it's 14y for some y. X and y are integers. Rearranging this slightly, this says that 5 is going to be 6x minus 14y. Of course, this number, this is an even number. This is 2 times 3x minus 7y. So therefore, 5 is even, which is a false and absurd statement. So to assume there's a solution leads to some absurdity. So the linear congruence (6x congruent to 5 mod 14), this has no solution. The first congruence we looked at, 6x congruent to 5 mod 13, has a solution. So what we conclude from this is that Some linear congruences have solutions and some don't. So we have the following problem.
Professor, could you re-explain this part again?
Sorry?
Could you re-explain this part again?
Yes. So here I have a different linear congruence, 6x congruent to 5 mod 14. I want to know if I can solve this congruence. And what I know is that if there's a solution x, an integer, that means that 6x minus y is divisible by 14. That means 6x minus y is 14. 6x minus 5 is 14 times y for some integer y. That's what it means to have a solution to this congruence. But this equation, if I rewrite it, says that 5 is 6x minus 14y. But this is even. It's an even integer. So if there's a solution, 5 is even, which is not true. It's absurd. So our hypothesis, our assumption, if there's a solution, leads to a false statement, so it can't be true. So that means that this linear congruence has no solution. 6x congruent to 5 mod 14 has no solution. The first congruence we looked at, 6x minus 5 congruent, 6x congruent to 5 minus mod 13 has a solution. For example, x equals 3 was a solution. So this suggests the following problem. Determine.
Thank you, Professor.
Yeah. Determine whether or when the linear congruence AX congruent to B mod M has a solution, right? If you started off in high school or wherever learning algebra, you were solving linear equations, quadratic equations. Now we're solving congruences. The simplest are always the linear congruences. And we see some linear congruences have solutions and some don't. And we like to know when a linear congruence does have a solution. And there's a very important theorem that completely solves this problem. So and the solution is the following. The linear congruence, AX congruent to B mod M, A is not 0 mod M, otherwise you don't have a linear equation, is solvable. That means has a solution if and only if D, which is the greatest common divisor of A and M, divides the number B, or equivalently, B is congruent to 0 modulo D, where D is this greatest common divisor. So let's just look at this in the context of the previous examples. I had looked at 5x congruent, 6x congruent to 5 mod 13. So this is A equals 6, B is 5, M is 13, D, which is the greatest common divisor of A and M, is the greatest common divisor of 6 and 13, which is 1. and every number is divisible by 1. So B, which is 5, is congruent to 0 mod D, mod 1, because 1 divides 5. So by this criterion, this congruence has a solution. The second one was 6x congruent to 5 mod 14. So here A is 6, B is 5, M is 14, D, which is the greatest common divisor of A and M, is the greatest common divisor of 6 and 14, which is 2, and B, which is 5, is not congruent to 0 mod 2. So this conclusion, this condition fails for the second congruence. Okay. So these two examples that we did a moment ago illustrate this theorem very nicely. So how do we prove the theorem? So AX congruent to B mod M is solvable if and only if there exists an integer y such that AX minus B is divisible by M is M times Y. Or if and only if you can write B in the form AX minus MY. And let's just look at this, for example, for a moment. So let D be the greatest common divisor of A and M. So D divides A, D divides M, so D divides AX minus MY, which is B, which means B is congruent to 0 mod D. So if there's a solution to the congruence, then B has to be congruent to 0 mod D. How do we prove the converse? Suppose B is congruent to 0 mod D. Well, we already proved, so by a previous result, if D is the greatest common divisor of A and M, then you can write D as a linear combination of A and M for some integers, x0 and y0. So if B is congruent to 0 mod D, then B is equal to D times Q for some Q in Z. Right. B is D times Q, but D I can write as AX0 minus MY0 times Q, which is AX0 Q minus MY0 Q. Suppose I let X0 Q, let me just call this X. So B is AX minus, I don't know, let Y0 Q maybe be Y. It's AX minus MY, or in other words, AX is congruent to B mod M. So if B is congruent to 0 mod D, the congruence has a solution. So that's the proof of the theorem. AX congruent to B mod M is solvable if and only if B is congruent to 0 modulo D, where D is the greatest common divisor of A and M. Okay. So this is really a very important result. And we can actually say something more precise. And this is another theorem. Suppose we have the congruence AX congruent to B mod M, and B is congruent to 0 mod D, where D is the greatest common divisor of A and M. So we know that this congruence has solutions. And in fact, you know that if an integer is a solution, every integer in the same congruence class mod M is also a solution. And we like to know how many solutions there are that aren't congruent to each other, pairwise incongruent solutions. So, and the answer is this congruence has exactly D pairwise incongruent solutions. Proof. Let's first consider the case when D, which is the greatest common divisor of an A and M, is 1. So we must show there's only one congruence class of solutions. We must show that if AX is congruent to B mod M, and AY is also congruent to B mod M, then X is congruent to Y mod M. And why is this? Well, just as we saw before in a special case, if AX is congruent to B mod M and AY is congruent to B mod M, then AX is congruent to AY mod M, which means AX minus AY is some multiple of M. And AX minus AY, that's A times X minus Y, is a multiple of M. But A and M are relatively prime, and M divides A times X minus Y. So M divides a product of two integers, this integer and this integer, and it's relatively prime to one of them. So again, by Euclid's lemma, M divides X minus Y, which means X is congruent to Y mod M. Actually, this special case, I'm just going to write down as a separate theorem, even though it's a special case. that AM of greatest common divisor 1, A is not 0. The linear congruence, AX congruent to B mod M, has a unique solution mod M. So maybe before we finish the proof of this theorem, you need to, right now, solve some congruences. Find all solutions of the following linear congruences. 5x congruent to 3 mod 7. Six x congruent to 2 mod 11. Three x congruent to 0 mod 5. So spend a few minutes right now looking for solutions of these congruences. And we know by the previous theorem that every one of these congruences has a unique solution with respect to its modulus. While you're doing that, I will maybe quickly check the attendance. Aldo Plumage, Amal Miawi, Espinal, Tapsoba, Alberto, Santiago, Duran, Hernandez, and Hernandez, Forch, Evariste, Gabriel Debray, no, Galileo Debray, Giassi, Sturgis, Sidibe, Sedano. Campos and Campos. Cruz. Rodriguez. Sar. Darame. Clark. Neil. Dar. Soto. Benitez. You. Okay. So what are the solutions? What is the solution to the first congruence?
7. 2.
2.
Yeah.
5 times 2 is 10. 10 minus 3 is 7. So x congruent to 2 mod 7, and any number congruent to 2 mod 7, like 9. 45 minus 3 is 42. Minus 25 minus 3 is minus 28. They would all work. What about the congruent 6x congruent to 2 mod 11?
4.
So if you let x equal 4, 6 times 4 is 24. Take away 2 is 22. Is x congruent to 4 mod 11. Can someone else give me a solution for the third congruence? What's the solution of this congruence?
It's 2, Professor?
2? If you let x equal 2, you get 6. 6 minus 0 is 6. Is 6 divisible by 5?
No.
It can't be 2.
Five over 3.
5 over 3 is not an integer. You're only looking for solutions in the integers.
There is no solution.
Well, what is 3 times 0? What's 3 times 0?
0.
So x congruent to 0 works. Mod 5. And anything congruent to 0 mod 5. Suppose you let x equal 5. You get 15. 15 is divisible by 5. So, but the least non-negative residue of a solution is 0. You know there has to be a solution because the theorem said there is. So the possibility of no solution in this case can't happen. Okay. Now, there's a refinement of this theorem that a congruence AX congruent to B mod M, if B is congruent to 0 mod D, D is the greatest common divisor in A and M. This has D pairwise incongruent solutions. And I want to skip that for now because there's a more important result I want to prove, which is the following. Let's take a example. Suppose let's say modulus M equal to 5, and I take A equal to 2. So I have 2. I want to look at the powers, the positive powers of 2. So I want to consider a congruence of the form A to the K mod M, as K goes from 1, 2, 3, and so forth. I'm looking at the powers of A. So here I'm looking at the powers of 2. So 2 to the first power is congruent to 2 mod 5, because 2 to the first power is 2. 2 squared is 4 mod 5. 2 cubed is 8, which is the same as 3 mod 5. And 2 to the fourth power is 16, which is 1 mod 5. So 2 to the K congruent to 1 mod 5 has the solution K equal to 4. This actually asks the following question. Find K, positive integer, such that A to the K is congruent to 1 mod M if it exists. So here, try this. Consider 3 to the K congruent to 1 mod 7. Find K. So you just have to start the calculation. 3 to the first power is 3 mod 7. 3 squared is 9, which is 2 mod 7. 3 cubed is 27, which is 6 mod 7. 3 to the fourth, well, I want to be lazy. 3 to the fourth is 3 squared times 3 squared. 3 squared is 2. This is 2 times 2. This is 4 mod 7. 3 to the fifth is 3 squared times 3 cubed. I'm just doing this so I can deal with small numbers. 3 squared is 4. 3 cubed is 6. So that's 24, which is that right? 3 squared is 2. No, 3 squared is 2. 3 cubed is 6. That's 12 mod 7. And 12 is the same as 5 mod 7. 3 to the sixth is 3 cubed times 3 cubed. That's 6 times 6, which is 36. And 36 is congruent to 1 mod 7 because 36 minus 1 is 35, is divisible by 7. So the smallest positive K is 6. Suppose we want to solve 2 to the K congruent to 1 mod 7. What's the smallest K that satisfies this congruence? Well, start checking. K equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just keep checking until you get a solution. When you let K equal 1, what is 2 to the first power mod 7?
2.
2. When you let K equal 2, what's 2 squared mod 7?
4.
When you let K equal 3, what is 2 cubed mod 7?
8. But
And what is 8 mod 7?
1 mod 7.
1. So the answer is K equal 3. 3 is the smallest power of 2. It's congruent to 1 mod 7. What about, I don't know, solve 5 to the K congruent to 1 mod 12. What's the smallest solution of that? What is 5 to the first power mod 12? What's 5 to the power 1?
5.
5.
5. What's 5 squared?
25.
5.
And what is 25 mod 12? You reduce everything mod 12 to the least non-negative residue. When you divide 25 by 12, what's the remainder?
1.
1. So that's the answer. K equal 2 works. 5 squared is congruent to 1 mod 12. 5 squared minus 1 is 25 minus 1 is 24 is exactly divisible by 12. What about 5 to the K congruent to 1 mod 13? Okay. Start to calculate the powers of 5 mod 13. I mean, 5 to the first power is 5. 5 squared is 25, which is the same as 12 mod 13. It's also the same as minus 1 mod 13. 5 cubed is 5 times 5 squared. That's 5 times minus 1. That's congruent to minus 5, which is the same as 8 mod 13. Minus 5 minus 8 is 13. 5 to the fourth is 5 squared times 5 squared. That's minus 1 times minus 1. Minus 1 times minus 1 is plus 1. So K equal 4 is a solution of this congruence. Okay, any questions about this? These are calculations with congruences, which you need to learn how to do. Right? Because this is a lot easier than, for most people, than proving a theorem about congruences. Okay, now, it's hard to find, it's actually hard to solve these congruences. I mean, first, we're using relatively small numbers, but at least there's an upper bound for the solution. And let me recall or state what is the Euler, it's a function, it's called the Euler Fee Function. Phi of m. So phi of m is the number of integers between 0 and m minus 1, integers a between 0 and 1 minus m, such that the greatest common divisor of a and m is 1. So let's sort of make a table. Here I'll write m, and here I'll write phi of m. So for 2, you're looking at the set of integers from 0 to 1. How many of these are relatively prime to 2? Well, just this one. So phi of 2 is equal to 1. What about phi of 3? So if I look at the integers of m is 3, I'm looking at the integers 0, 1, 2. How many of these are prime to 3? Well, 1 and 2 are. So there are 2 of them. What about 4? How many of these integers are relatively prime to 4? Well, 0 and 2 have a common factor of 2, but 1 and 3 don't. So phi of 4 is also equal to 2. What about 5? So I look at the integers from 0 to 4. These 4 are all relatively prime to 5, so phi of 5 is 4. You know, this is kind of fun. I'll make a table up to 10. What about 6? You look at the integers 0 up to 6 minus 1. 1, 2, 3, 4, 5. Which of these are relatively prime to 6? Well, only 1 and 5. The other numbers have a common factor with 6. So phi of 6 is 2. For phi of 7, we look at the numbers from 0 to 6. 6 of them are relatively prime to 7. So phi of 7 is 6. For 8, you look at the integers from 0 to 7. Which numbers are relatively prime to 8? The odd numbers. 1, 3, 5, and 7. So phi of 8 is 4. What about 9? You look at all the numbers up to 9 minus 1 or 8. If a number has a factor in common with 9, it's divisible by 3. So the numbers that are relatively prime to 9 are the numbers not divisible by 3. 1 and 2, 4 and 5, 7 and 8. There's 6 of them. You let m equal 10, you look at all the numbers up to 9. If a number is even, it has a common factor with 10. If a number is divisible by 5, it has a common factor with 10. The ones that do not are 1, 3 and 4, 7, and 9. And there are 1, 2, 3, sorry, not 4. 1, 3, 7, and 9. So phi of 10 is 4. Okay. So this is a very important function in algebra called the Euler Fee Function. And what is a very important theorem in the history of mathematics, which was proved first by Fermat and then extended by a mathematician whose name is spelled E-U-L-E-R, but is pronounced Euler. And it says that if A and M are relatively prime, A to the power phi of M is always congruent to 1 mod M. Doesn't say that phi of M is the smallest power, but at least it does give you a power that works. And for the proof, well, you have to remember, what is the Euler Fee function? So phi of M is the number of integers between 0 and M minus 1 such that A and M are relatively prime. So that's denote these integers R1, R2, R3, up to R sub phi of M. So this is what's called a reduced system of residues mod M. It's a complete set of representatives of all the congruence classes that are relatively prime to M. Now, so Ri and M, the greatest common divisor is 1 for all I going from 1 up to phi of M. And we also know that A and M is 1. So Ri is relatively prime to M and A is relatively prime to M. So by Euclid's lemma, once again, AR sub I is relatively prime to M, because if there was a prime that divided both of these numbers, it would divide ARI, it would divide M, and it would divide one of these. And so one of these conditions would have to be false. So ARI is congruent, is relatively prime to M. So there exists some number J between 1 and phi of M such that, well, this is a number relatively prime to M. This is a complete set of representatives for all the numbers relatively prime to M. So ARI is congruent to some RJ mod M. So given I, ARI is some unique J. J is some function, I call it sigma of I. Right? So ARI is congruent to R sigma of I mod M. So let me just repeat that statement again. For every I between 1 and phi of M, there exists a unique J equal to sigma of I, an integer between 1 and phi of M, such that AR sub I is congruent to R sigma of I mod M. So this is a series of congruences. We have AR1 congruent to R sigma of 1 mod M, AR2 congruent to R sigma of 2 mod M, and so forth. A R phi of M congruent to R sigma of phi of M mod M. And you can multiply congruence classes. Multiply these congruence classes. So on the left, we get AR1, AR2, AR3, up to AR phi of M, congruent to R sigma of 1, R sigma of 2, R sigma of 3, R sigma of phi of M mod M. And now we just stare at this equation. On the left side, we have factors of A for each one of these terms. I can factor it out. How many terms are there? There are phi of M terms. How many A's are there? There are phi of M A's. So if I factor this out, I get A to the phi of M times the product of these R's is congruent to, well, here, multiplication is commutative. As I look at sigma 1, sigma 2 up to sigma phi of M, that's just the numbers 1 up to phi of M in some order. So rearranging, this is also R1, R2 up to R sub phi of M mod M. And this number here is the same as this number here. And it's relatively prime to M, so I can cancel it. And I get A to the phi of M is congruent to 1 mod M. If A and M are relatively prime. So this is the famous Euler Fermat theorem. Let's just look at a couple of examples. So if A and M are relatively prime, then A to the power phi of M is congruent to 1 mod M. Let's take M equal to 5. And phi of 5 we calculated is equal to 4. So in this instance, in this special case, if A is relatively prime to 5, then A to the 4th power is congruent to 1 mod 5. So what are the congruence classes, or the numbers relatively prime to 5, up to 4, 1, 2, 3, and 4. 1 to the 4th is congruent to 1 mod 5. 2 to the 4th. 2 to the 4th is 16. It's congruent to 1 mod 5. What is 3 to the 4th? It's 81. 81 is congruent to 1 mod 5. What is 4 to the 4th? See, 4, 16, 64, 256. Subtract 1, you get 255. That's congruent to 1 mod 5. So this is the Euler Fermat theorem for M equal 5. What about M equal 6? Phi of 6 is 2. And A is relatively prime to 6, only if A is 1 or 5. 1 squared, congruent to 1 mod 6. 5 squared is 25. Subtract 1 is 24, is divisible by 6. So 5 squared is also congruent to 1 mod 6. Okay, so this is the Euler Fermat theorem. All right, well, we're moving along, doing a lot. That's good. What I think I'm going to try to do from now on Class always starts at 9 o'clock, but I think I'll log on every day 15 minutes earlier at 8:45. So if you have questions about anything, there's an extra period of time when you can ask me some questions. And I mean, it's completely up to you, but it's just like, I'll just log on 15 minutes early. So I'm available to answer questions from now on. Okay. Any questions about any of this so far? If not, then we are done for the day. Okay,
All right, have a nice day.
thank you. It's supposed to be beautiful today and tomorrow, so enjoy the fresh air if you can. Bye all.
All right, thank you.